So, to summarize, at the end of the day on Tuesday, or the period on Tuesday, we're discussing the various plots that we were getting. We had, what was it, radius versus atomic number, right? And then we had, what was it? Was it radius again?
No, it's
ionization energy. Okay. The first one was pretty darn easy. We were doing a group trend. Okay, and we found out in general that as atomic number increased within a group, that the radius increased also. Would anyone like to offer a nice, succinct, valid explanation for that? Mandy.
When there's a bigger atomic number, there's more electrons filling more energy.
And there you go. There are more electrons as atomic number increases because, for the reasons you said, and those electrons are going into more and more energy levels, which are further from the nucleus. So if you guys remember, it was one of these ideas with the arc diagrams. More electrons, more energy levels, greater radius. Hi, who are you? How are you? Uh-huh. Yeah, it's over there in the middle rack, possibly. Middle tray. Unless it's this one, which it's not. Okay, so that one was pretty darn easy. I think everyone felt pretty comfortable with that. In the second, period or graph, we were looking at the radius trend within a period. And we discovered that as atomic number increased within a period, atomic number decreased. There is a nice, valid explanation for that. I introduced an equation to you, or a law to you. Does anyone remember that law? Coulomb's law. So if you remember Coulomb's law, the force of attraction between or force of repulsion, but in this case it's attraction because we're talking about electrons to the nucleus, is proportional to the product of two charges and inversely proportional to the distance between those charges. Okay? So, since we're talking about the same period, we're talking about the same energy level. And was it period 3, if I remember right? Or was it period 2? Period 3. So we were talking about the elements in period 3, which means we were referring to the third energy level, for at least the beginnings of the third energy level. Okay? And what's happening is the nuclear charge is increasing. So Q2 possibly is increasing. Whereas Q1, it's also increasing, but we're talking about individual electrons, and these electrons aren't influencing each other very much other than repelling each other. So as the number of protons is increasing, each of those electrons, all the electrons in the entire atom, are more attracted to the nucleus, which means are going to be pulled more tightly. Similar to magnetism, but not the same. Similar, but not the same. Okay, so the distance in this case from the nucleus is saying essentially the same because we're all on the same energy level. It's the nuclear charge that's increasing significantly. Does that make sense? These two ideas are huge. They explain everything else we're going to be talking about. So you have to have a very good knowledge of that. Okay. Moving over then. Once again, Coulomb's law is going to be invoked here quite a bit. Now we're talking about ionization energy, and if you recall, once you guys finally discovered where the definition of that was within the actual discussion in the packet, that's the energy required to remove an electron from an atom. Why does it take energy to remove an electron? Because they are attracted to the nucleus. Okay? The greater the attractive force, the more energy you would think would be required to remove the electron. Okay? So, in this case, we're going, I believe, again, a group trend. Is that right? Okay? And then we found out that within a group as atomic radius, or sorry about that, did we do this right? Yeah, atomic number. What am I doing? As atomic number increased, the ionization energy decreased. What could possibly be an explanation there? Go ahead, Sam.
There's not energy levels in that.
This would be a wonderful place to start.
Well, because it's in a group, you're adding energy levels.
And so the distance is increasing, therefore the force of attraction is decreasing, and therefore it would require less energy to remove electrons. There's a smaller force of attraction for those electrons. Yay? Okay. And then we're looking, in the last one, we're looking for ionization energy versus atomic number in a period. Now, this, I don't know, did we ever get to this one actually on Tuesday? We may not have. I'm pretty darn sure we got to here. Yes or no?
I don't know.
We did not get to that? Oh, so this is our first time here?
Yeah.
Okay. So, once again, after we invoked Coulomb's law over here for the radius versus atomic number, we can apply that to this idea here. There are more energy levels, as we discovered, because we're in a group. As atomic number is increasing, we're adding more and more energy levels. Okay? And because the distance is increasing then, that force of attraction is less energy to required to remove the electron. But in a period, and this trend was not nearly as, what should I say, smooth, there are reasons for that little jaggedness. If you would love to talk about that some other time, we can. But in general, and there was someone or two people, and I can't remember. There was at least one, if not two, and I can't remember which group, whether it was this group or my ninth grade group, where someone did like a best fit line. I thought, oh, that's the first time, seriously, in 20 some odd years, that's the first time I've seen somebody do that. Was that anybody in here? Was that you? Okay, you were it. So let me see. Let's say on average 4 chemistry classes a year times, say on average 22, 23 students per year for 25 years. That's a lot of students. You're the only one that's ever done a best fit line. Okay, so anyway, but in general, would you agree that there was an increase, there was a positive slope? Nobody's agreeing. Ryan, what do you think? Okay, in general. There's some deviations, reasons for those, but in general, positive slope, which means there's a direct relationship, which means that ionization in energy, or the energy required to remove an electron, is directly related to the atomic number, meaning as we go across the period, the amount of energy required to remove the electron increases. Would anyone like to offer an explanation for that? Besides Josh, right now. We'll come back to you when nobody else... Ah! Addie, who hasn't been here for 14 days. Go.
Well, because as the electrons are being added to one energy level, the force of attraction increases because the distance gets smaller. No, the distance gets smaller because of the force increases, so then it's going to be harder to get the electrons.
Why does the force increase?
Because more electrons are being added.
Ah, no. Because we're talking about removing one electron. It could be this one, it could be this one, it could be this one, it could be that one.
Because the radius is smaller.
Okay, yes, yes.
Force of attraction, so it's harder.
Nuclear charge is increasing.
Yeah.
Yeah, oh yeah, that too. Okay.
The force of attraction is increasing. Isn't that the nuclear, the same thing?
No,
It isn't?
no, not necessarily. It could be, okay, would this electron have a greater force of attraction than this electron?
Yes.
Why?
Because it's closer.
Boom. So you, okay. There's two factors we have to consider, but since we're in a period, the energy, the distance from the nucleus is very similar, essentially the same. What is increasing, though, is the nuclear charge. I'm going to let these ideas soak for a little bit. They need to soak for a little bit. Okay. With all this that we've discussed being presented, let's summarize a little bit. Where on the periodic table would we expect to find, in general, the largest atoms? Got this whole big periodic table. In general, where are we expecting to find the largest atoms? Josh, go ahead. The more left. You're halfway right. And down, the bottom left. Would you guys agree? Does that make any sense? For 5 of you, it does. For the other 16 of you, here's why. As you go down a group, what happens to the size of the atoms? They get bigger. Hence the bottom part. I believe you were the bottom part, right? As you go across a period, what happens to the atoms? They get smaller, therefore they start off larger. So, in general, bottom left is where you find the largest atoms. With that being said, here's the easy answer. Where on the periodic table would you expect to find the smallest atoms in general? The upper right. Because once again, they start off small, get larger. They start off large and get smaller. So in this general area, we're expecting to find the smallest atoms. And just for fun, what do you think the smallest atom is? Neon, I heard. Did you forget one? It can belong one of two places. Therefore, so can hydrogen. But doesn't matter where it is on the periodic table. Why would this be the smallest? Okay, it has the fewest energy levels, 1, and the greater nuclear charge. It has a greater nuclear charge than the hydrogen does. Okay. Ionization energy. Did you take a picture of that?
What?
Nothing. See, ionization energy. Where on the periodic table would we expect to find the atoms that require the least amount of energy to remove them from the atom? Or in other words, lowest ionization energy. Ben is pointing to here. I saw you point here. I don't know what he was pointing at. What do you say? The top left, he said, would have the highest or lowest ionization energy. He's half right. What's that? Bottom left. Wouldn't it be down in here? Why is that? That's where the atoms are the largest, okay? The least nuclear charge as opposed to the right-hand side, and the furthest from the nucleus. Where on the periodic table would we expect to find the atoms that would have the greatest ionization energy or require the most energy to remove an electron? Upper right, because they're in a position where there's the most nuclear charge and the smallest, closer to the nucleus. So it increases as you go like this and decreases as you go like this. Whereas radius where would you expect to find the largest? So what could we say about the relationship between ionization energy and radius? How are they related? Inversely related. You haven't been here for 14 days either, but you get inverse relationships, don't you? Yeah. Listen, it's going to take a couple days for this stuff to soak in your brains, okay? I get that. But we'll have to have it done by Friday for our test. Hi, Addie.
So for this test, you said that we have to be able to explain why.
Yes, so you were here to see a copy of when I showed everyone a copy of that, right?
Yeah.
Yep.
But I don't think I could explain why when the atomic number goes higher, the radius gets smaller. For instance.
Very good. Because of this right here.
Yeah, I don't think I understand that.
Okay. Okay. What do the Q's stand for? Excellent. What does the D stand for? Take a stab. Okay, the distance from the nucleus, which, as it turns out, in aspherical, that's a radius, right? But the distance from the nucleus. Okay? So, let's imagine we're talking about an electron. Okay? And if we're in the same energy level, this distance essentially, whoops, sorry about that, that's where the nucleus is essentially the same. It's not exactly the same for reasons we're about to discover, okay? But there's a big difference between here and here, and here and here, right? Would you agree with that? Okay? So really the only thing that's changing is the nuclear charge, the amount of protons in the nucleus.
Okay.
Right?
Yeah.
And if you can imagine, if you ever played, and again, this is similar. It's not exactly the thing, but it's the same, but it's similar. You've played with magnets before, okay? If you have one magnet in each hand, is there a force of attraction?
Yeah.
If their opposite poles are next to each other. If you have 4 magnets in each hand, is there a force of attraction?
Yeah.
And how would you describe that force of attraction relative to the first scenario?
So
Because there's a greater charge.
okay. So when there's more
in the same energy. Now, when there's more protons,
But the number of protons doesn't change, does it?
as you go across the period, you
Oh,
better
yeah.
darn believe it does.
Okay. So it's not talking about like how the electrons move. It's talking about.
No, because you're considering each electron and its force of attraction to the nucleus.
Okay. Okay, that makes
Is that better?
I was thinking about like when you add electrons to one energy level, but it's not really, it's focusing more on the proton.
Well, yeah.
Okay, I get it.
Is that better now?
Yeah.
You just helped 6 other people. They thank you. Right? All right. Right? No. You already knew that? Yeah, well, that happens after Thanksgiving. Okay. That's all I got for atomic trends. Atomic trends. We talked about the isoelectronic thing, didn't we? I know we did. Osmosis?
Oh, yeah.
Yeah. Okay. This is going off the packet now, because theoretically it looks like we're done with the packet, right? But we're not done with the trends. We've got more. Oh, wait, there's more. This, you can either, I don't know, there might be a page on the back of your note, that packet that's blank, or you can add it to your notes. In your book, okay? Now, we already were introduced to the idea that what is an ion in general? An atom that has a charge due to the loss or gain of electrons, right? But then we had a further discussion, we had a discussion earlier in the year, but we also had a discussion, I believe it was Monday, when I was going through the first half of that packet. We remembered that metals have a tendency to lose valence electrons to form what charge? Positively charged ions, whereas nonmetals have a tendency to gain electrons and form negatively charged ions. And if you guys recall, to be able to tell the difference where metals versus nonmetals are is this stair step or zigzag line. You guys remember this? Okay, everything to the left of this are metals, where everything to the right are nonmetals. Okay. With that being said, there's also going to be trends for the radii on these. It might not be a bad idea for you to have a fresh piece of paper and then rotate it 90 degrees. Entirely up to you. Oh, let's call this, just for fun, lithium. This one's sodium. We'll call this one, what are we going to call this? Beryllium. And call this one calcium. And then over here, I don't know, I guess we'll go to oxygen here, which makes this fluorine, and then over here that makes this sulfur, and that makes that chlorine. Would you guys agree? I'm just randomly picking various elements within both 2 different, or actually 3 different periods, and a couple of different 4 different groups. Okay? by doing just this random set here, somewhat random set here, we'll be able to get what's going on. Now, remember that lithium has 2 electrons and 1 valence electron. Sodium has 2, 8, and 1 valence electron. Would you guys agree? Beryllium has 2 and 2, and calcium has 2, 8, 8, and 2. Oxygen has 2 and 6. Fluorine is 2 and 7. Sulfur, 2, 8, and 6. Chlorine, 2, 8, and 7. Everyone hunky-dory so far? If we need to add more atoms, we will, but for now, this should be good. You know what? We are going to add another one. We're going to add another one probably here. Probably here, but we'll see what happens. Okay, so now, what is lithium going to do when it forms an ion? It's a metal, so it's going to lose 1 valence electron. What is sodium going to do when it forms an ion? Lose 1 valence electron. What is beryllium going to do? Lose its 2 valence electrons, whereas calcium is going to lose its 2 valence electrons. Okay, just for fun, how would we describe the ionic radii for metals versus their atomic radii? They got smaller. Why did they get smaller? They lost electrons from an entire energy level. That's kind of a duh, no-brainer one. Would you guys agree with that? Okay, so for metals, their ionic radii are smaller than their atomic counterpart, the neutral atom counterparts, because an entire energy level is lost. So far, so good? Now, what would you say about the general trend in ionic radii as you go down a group, though? They get larger, just like they did before. Would you guys agree? Remember, the group trend for atomic radii were to get larger also because there are more electrons and more energy level. That idea stays the same. It's just that they're smaller than they were for the atoms. The group trends are pretty darn easy, aren't they? It's the period trends and that whole idea of applying Coulomb's law that starts making things a little interesting. All right. Now, let's think this one through. Let me change this a little bit because you guys can't see it very well. How many protons does an atom of lithium have? Yep. How many protons does an atom of sodium have? 11. Okay. And beryllium has 4. Which of these is larger? I'm going to call on someone. I'm giving you some wait time to contemplate. Charcy, which one do you think is larger? The lithium ion or the beryllium ion? Why? Why? There you go. So the same reasons as before. Would you guys agree? So far, nothing's really changed when we've talked about ions, at least for the metals anyway. They get larger as you go down the group because there's more energy levels. They get smaller as you go across the period because there's an increased nuclear charge. And the electrons are in the same energy level. So far, so good, right? Okay, let's kind of draw a line and start talking about the nonmetals. Nonmetals, as we just discussed, have a tendency to gain electrons when they form ions. So, oxygen has 6 valence electrons. How many electrons is it going to gain? 2. To complete that energy level, to complete that octet. What's sulfur going to do? Gain 2 electrons to complete that energy level. Just for fun, not that we've done a lot of things with this. Yeah, we've done enough. What will the charge on these 2 ions be? 2 minus, right, because they both gain 2 electrons. Okay, just reviewing that really quickly. It's been a little while since we've done that. Okay, so now, what's fluorine going to do? Gain 1 electron, and therefore its ion is going to have what charge? 1 minus. And chlorine's going to gain 1 electron and also form a 1 negative charge for all the reasons we've talked about before. Okay, so now, going down the group, what's going to happen to the radius of the ions? They're going to increase, just like they did before. Greater number of energy level, more electrons, more energy levels further from the nucleus. So far, so good, right? What's going to happen to the size of the ions as you go across a period? And remember, oxygen has 8 protons. Fluorine has 7 protons. Wait a minute. 9 protons. Sulfur has 16 protons. And chlorine has 17 protons. What's going to happen to the size of the ions as you go across the period? They're going to get smaller because there's an increased nuclear charge. The number of electrons, remember these are isoelectronic. This has, how many electrons is this going to have now? 10. How many is this one going to have? 10. This one's going to have? Thanks for doing the math. 18. This one's going to have 18. Everyone good? So if they're isoelectronic, what's the only thing that can influence their radius? The number of protons. This has more protons, therefore those electrons are going to have a greater force of attraction due to Coulomb's law. Brought in more tightly. Same thing here. Would you agree? So once again, the period trend seems to be maintained with the ions. However, how is this radius going to be, the ionic radius, going to compare to the atomic radius for oxygen? Kirsten seems to think the ionic radius is going to be larger than the atomic radius. Would anyone concur with that? Ryan concurs. You think it would be smaller because there are more electrons. I'm going to have you do a favor for me. Could you take your chair and go sit in between Allie and Charcy, please? Now, everyone watch what happens to Allie and Charcy. Where are you going? I'll find out. What are you guys going to do? Oh, look at this. Look at that. What happened? Why? what's the charge on an electron? And how well do the electrons like other electrons? They don't. So as these two electrons get added to the same energy level, the force of repulsion is going to increase and the radius will get slightly larger. Now that's different, isn't it? Because over here we found out the ionic radii got smaller because we lost an entire energy level. Over here, on the nonmetals, the ionic radii are getting larger because of the force of repulsions between the added electrons. And it's all happening in the same energy level, which we're going to get to here in a second. But, once again, same thing's going to happen over here, right? There's going to be increase in radius due to, relative to the atomic radius, but this is going to be smaller than that because of the increased nuclear charge, which we had already talked about. So far, we've seen that the ionic radii get larger as you go down the group, for all the reasons we talked about. Got smaller as you go across the period because of the increased nuclear charge. Got for the nonmetals, larger down the group because there's more energy levels, more electrons, more energy levels. Got smaller across the period because of the increased nuclear charge. But what's the problem? We just got done saying these atomic or ionic radii are smaller than their neutral counterparts, but these ionic radii are larger than their neutral atoms. So what's the general trend as you go across the period? Well, as it turns out, there kind of is no general trend. Because what happens? Let's talk about sodium. Third period. Magnesium. Now we're talking ionic radii. What's magnesium going to be relative to sodium? Smaller. What's aluminum going to be relative to magnesium? Smaller. Because it loses its valence electrons and there's increased nuclear charge. What's silicon going to be relative to aluminum? By a whole energy level. Why? And silicon gaining electrons, right? So we went smaller, smaller, smaller because we lost an entire energy level and increased nuclear charge. But over here, we're gaining electrons and kept that same nuclear, or that same number of valence electrons. But then, after silicon, what's phosphorus going to do? Smaller. Sulfur, smaller. Chlorine, smaller because of the increased nuclear charge. So for ionic trend, smaller, 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 big, smaller, smaller, smaller. Because we went from losing electrons to gaining electrons. Right?
Yeah.
Hi. Everybody keeps waving to me. Hi. Well, okay, we're going to kind of leave. Yeah, I know. But again, you go back to the transition from metals to nonmetals. Theoretically, yes. Boron's kind of weird, but yeah. That's why I have a tendency to stick a little bit more a little bit lower. How are we doing? Listen, anybody have a headache?
I have a constant headache.
You should, a constant headache? Okay, well, you don't count. Right. Your brain should hurt right now a little bit. Does your brain hurt a little bit? Rowan? No. She just has a little tear coming down. How are you doing here? Does it? It's weird, isn't it? How that makes sense?
Why does it not make sense?
Okay. Look at Alyssa. Does it make sense when I say it? We're not there yet to the point where everybody's able to do it on their own. Cameron, how's things going? You've just sat there with that little smile on your face the entire period. You haven't. I don't know what that means. I think these two are going to be in really good shape when they get back. All right. I would like you to turn to page, I actually guessed right with my other group, 151. I may or may not be right. Oh my gosh, I was right again. 2 times in a row. On page 151, you'll see a handy-dandy little periodic table with a bunch of green blobs on it. Can I explain to you what the green blobs represent so you can actually follow along, Ben?
Yeah, that's what I'm going to say.
Not listening, is he?
That's just the one.
Ben, what do the green blobs mean? Excellent. Or atomic radii, but either way, same thing. Okay, so this is the I want to emphasize here. This is the atomic radii. We're going back to the beginning of the period, okay? As you go down a group, what appears, any group, pick a group, any group, what appears to happen to the size of the atoms as you go down the group? They get larger. For all the reasons we talked about, more electrons, more, oh, hold on. That's a nice suggestion for me to end class. Now, as you go across a period, any period, what appears to be happening to the size of the radii? They get smaller. For all the reasons that we talked about. Where does the smallest atom appear to be? In the upper right. Where does the largest atoms appear to be? For all the reasons we discussed. We will look at that tomorrow with the ionic radii. Yeah. Yes.